Ever wonder how scientists figure out what happened deep underground during an earthquake? It's not like they can just, go down there and take a look.
Nope. It's all about the data. Seismic waves are our clues, you see.
So this paper, Rapid Source Inversions of the 2023 SE Türkiye earthquakes, it's all about using those waves to quickly understand those devastating earthquakes.
They use two types of data, teleseismic from far away and strong motion from closer to the epicenter.
So like getting a big picture and then zooming in for the details. Right, so what's the difference between teleseismic and strong motion data?
Teleseismic data comes from seismic stations far away, giving a broad view of the earthquake's rupture. Strong motion data is from closer sensors, providing much higher resolution.
Like a wide-angle lens versus a close-up shot?
Exactly. The teleseismic data gives you the overall picture. The strong motion data fills in the finer details.
This paper focuses on a doublet 2 major earthquakes hitting the same region.
Yeah, a Mw7.8 followed by a Mw7.6. Pretty intense, huh?
And how did the inversions reveal the differences between these two quakes?
The first one was bigger, longer, and lasted longer, but its peak moment rate was lower than the second one.
So what did the rupture models show?
The first quake ruptured asymmetrically, mostly to the northeast. The second was more unilateral, mostly westward.
And how did the strong motion models compare?
They showed more detail. For the Mw7.6 quake, the strong motion model showed a bilateral rupture, not just unilateral, but the main direction was still westward.
That's interesting. Were the models consistent overall?
Yes, remarkably so. Both types of data agreed on magnitudes, durations, and main rupture directions.
So both methods are useful?
Absolutely. But strong motion data is better for emergency response because it's available faster and offers higher resolution.
Let's recap the key points. Fast inversions using both teleseismic and strong motion data were performed.
The first quake was larger and longer, but with a lower peak moment rate.
Strong motion models provided higher resolution, showing a bilateral rupture for the second quake, but the main direction was still westward.
Both data types gave consistent results, but strong motion data is preferable for rapid emergency response.
What are the broader implications of this research?
It shows the value of combining different data types for rapid earthquake analysis. It also highlights the potential of strong motion data for faster, more detailed emergency response.
What's next in this area of research?
Improving the speed and accuracy of these inversions and incorporating even more data types, like GPS and INSAR.
The paper mentions a conflict of interest.
Yes, two of the authors are on the journal's editorial board, but they weren't involved in the review process. Transparency is key,
The paper has a pretty extensive list of references.
It builds on a lot of previous work in earthquake science and source inversion techniques.
And there are related articles listed as well.
Shows the ongoing research in this field with other studies using similar techniques or focusing on related earthquakes.
The paper has already had quite a few views and downloads.
Shows the interest in this research, especially given the significance of the earthquakes studied.
The paper includes several figures and tables.
Visualizing the data and results is crucial for understanding the complex processes involved.
So this paper provides a really valuable insight into how we can quickly understand major earthquakes.
It's a great example of how combining different data sources and advanced techniques can lead to a better understanding of these devastating events.
That was a great discussion. Thanks for sharing your expertise.